Hi, welcome back after the break. Coming up next, we have a panel around the topic. Do advanced SoC architectures and challenges demand new tools and approaches? The panel will be moderated by Nick Heaton, who is an ASIC and EDA veteran with more than 30 years experience. He graduated from the Brunel University, London in 1983 with first-class honors in engineering and management systems. He works in the systems and verification group at Cadence and is responsible for SoC verification. He currently holds the position of Distinguished Engineer and SoC Verification Architect. Over to you, Nick.
Hi, hello everybody. Thank you, Shreya, for that introduction. In the last few years, we've seen a real explosion in computing innovation. Some people say we're in a golden era of SoC architecture, and there are many innovations giving choices to the designers. Domain-specific compute, multi-layered cache architectures, virtualization, high-speed I/O, multi-die chiplets. There's tons of new options coming to the designers as really to address the end of more scaling. And this is all great. Unfortunately for the verification engineers, there's a price to pay for all of these innovations in that they can throw up new challenges which have not necessarily been encountered before. So today we're going to be discussing the current and the future challenges that these verification leads are experiencing directly, how they're going about approaching these challenges, and what emerging and future technologies and approaches that we might need in the verification space. So with that, I'd really like to welcome all the panelists and invite them to introduce themselves. Nirmal, welcome, and could you please introduce yourself?
Hey, thanks, Nick. Hope I'm audible.
Yep.
Hey, I'm Nirmal from Qualcomm. Have 20 plus experience in the design and verification overall. The last 8 years, I've been focusing on SoC verification for the mobile, compute, and auto chips, primarily leading teams for the systems and low power aspects of the SoC.
Thank you, Nirmal. That's going to be really fascinating to hear your insights into these problems. Sukumar, can you please introduce yourself?
Sure. Thank you. Thanks for that, Nick. I'm a lifetime Intelite. Currently I do server verification. I'm a verification architect for the server organization here, and I've been doing verification pretty much all my life, starting with phones and tablets and clients and IoTs and wearables and graphics and now servers.
Great, thanks for that. And Pankaj, please introduce yourself.
Hello everyone, yeah, I'm Pankaj Kakkar, working for Cadence and managing the product engineering team as part of the system verification group, responsible for system level verification, software bring up, and safety verification solutions at Cadence. I've been in the industry for close to 21 years now, after graduating out of IIT Kanpur. So,
great, thank you, Pankaj. So, what I want to start this discussion and kick things off really is to just firstly explore the space and the challenges you're facing, whether specific domains, that kind of thing. Nirmal, do you want to go first with this?
Yeah, so to start off with, the current domain challenges is the confluence of the transistor density, storage density, and the connectivity, right? So we have all of this growing year after year, and we have come to a place where we have big data, the cloud and the edge, where everything is trying to meet. So definitely, our primary, domain challenges today, if you ask me, is the rise of the machines or the AI engines, which is growing like every year. We are putting so many AI data workloads and data engines which are going into the chips. So this AI engines, the problem is itself, the verification of them is the workloads are going to be quite unpredictable. Unless we go to the application, we are not able to understand the workloads. So this takes us to our traffic modeling primarily. So how do we put these workloads which are growing every year, which is required for this machine learning and the data usage. There are multiple applications which we have started using this, starting from video, audio, and low power. The multiple places these AI engines are playing a critical role. The other area the domain which we are facing quite a challenge is on the system level performance. Specifically, I think way back about a decade back, we started putting a single camera into the mobile phones, but now we have a minimum triple camera. So the 3 cameras, the real use case application is, earlier we used to worry about only image stabilization, where a user is trying to capture a video or a photo, and we want to make sure the video or the photo is stabilized and it's in a good form to view. But now with triple camera, so we try to capture multiple views, and we try to process them and get the best to the user. So this performance has been scaling, and this is going to go scale more with the metaverse, where we start putting the virtual reality and the digital living, where we start creating the virtual spaces. And one more thing, definitely the coherency with so much compute. I think that the low power systems today have this big little architecture which are becoming standard, and the software applications need the low power and low latency systems to realize complex applications. So those are my top 3 domain challenges. Over to you, Nick.
Cool, thanks. So I hear, modeling workloads is problematic, measuring the performance, problematic coherency, low power. So these are pretty big. Each of those is big ticket item. Sukumar, would be great to hear what kind of challenges you're facing.
Sure. Don't be surprised if I'm going to repeat the same thing, right? For practical
purposes. That's interesting, because you're working in different domains, right?
That is true. That is true. I was listening to Nirmal. I'm like, my verification challenges are probably very different, but then quite similar in terms of the domains, right? So if you start out, so the problem started, a decade ago when we started partitioning IPs, right? We started putting in all the various different IPs, and then we called it as SoC and said, go, right? So from a verification engineering perspective, the challenge is the system level architecture, right? So what we ended up doing is this distributed model, which is a good thing, by the way, right? Because you have really small pieces of logic that you can actually go verify, right? But at the end of the day, if you want the chip to work and you don't want really bad bugs, you want to make sure everything actually talk together well, and then they actually know each other quite well, right? That relationship is important. So the challenge truly, that I see is the system level architecture definition, right? From a domain perspective, that starts off, your bare bone coherency is your domain, right? Your resource sharing is distributed, right? You have your mesh, you have your cache, you have your core, you have your agents, you have your fabric. So that in itself to actually talk to each other is a big challenge, right? So that's the first one. As an extension of that, one of the biggest challenges today, and the reality is because the market and the business demands that, our performance validation is a huge challenge, right? To a large degree, you can start verifying a piece of logic inside a given IP, let us say, or a smaller subsystem. But the reality is you have an architecture model, the architect comes and says, look, this is what I believe this chip should behave like from a performance perspective. Well, he or she is way off, is what you find out. But how do you find that out? That's the biggest challenge, right? Because to actually put every component and then actually build a full chip model and then go say, okay, so I'm going to actually make sure that I'm going to tape in this project after I make sure I hit all these performance numbers, is just incredibly tough because multiple different things, right? And then that's where we get into the methodologies, how we do verification. Simulation is very slow, the models are very big. So those are the real, bare bone grassroots challenges because of the performance validation that performance validation brings about, in addition to all the architecture challenges that we are talking about. And of course, the third one, which I don't know if this will ever go away, is the power management, right? Again, there is a problem of distributed systems and distributed architecture that we talk about, right? You have, let us say, a centralized power management unit, but then you have a controller, you have a PHY, you have the handshake between all of them, right? And then, of course, the complexity that the UPF itself brings in. So these three, again, I mean, there is, of course, the fourth one, which I kind of, we all neglect, but we don't, is the security aspect of it. The security is a big deal, but I don't know if I want to really call that as a verification problem in itself. Security today and tomorrow probably is going to be the most important domain. But then that spans the whole plethora of architecture, RTL integration, and verification, right? And of course, also. So that's kind of my story where I stand.
You said a couple of things that are really interesting to me there. You said architects believe, and I think what that tells me is verification people disbelieve, right? It's like
that's the job profile, right, Nick?
we're kind of the reality check for the architects, right? Pankaj, can you give us some insight into the kind of challenges you see?
Yeah, I think I echo some of the similar sentiments as Sukumar and Nirmal said, with respect to the verification complexity ever growing and with the time to verify and tape out the chip not really increasing. So, and with performance and then really making sure that your SoC and system work in the context of the real software, right? In the sense that I mean, you can verify your IPs or your SoCs with models or with whatever artificial stimulus you can create. But ultimately, what customers are really trying to do is to verify it in the context of the real software that runs, because those workloads are very different. And being able to do that brings in a big challenge in hardware software co-verification, and a lot of customers are really trying to do that early in the cycle so that if there are problems being found, they are able to fix it, and the cost of fixing is less, right? I mean, the earlier you find, the easier is it to fix. So I think that is a big challenge. And of course, all the complexity with coherency, with low power, with high speed serial interfaces, with AI ML logic coming into play adds to this.
Right, and so the interesting thing is when you're talking there about software and hardware, I guess the real big worry is you're debugging two unknowns together, right? The hardware isn't necessarily bug-free, software isn't bug-free. If you can make one of those less buggy, you improve your chances of debug. Because one of the things I think Sukumar, it touched on what you said, touched on me. Well, firstly, analyzing performance, for example, is hard. But then how do you debug the problems as well, which is kind of the next level issue. So, the tools can come along to give you the insight, but you then need to go and actually debug on a very complex system as well. So I think there's going to be, we're going to talk about emerging technologies in a minute, but, I think that sort of leads you to this question about debug becomes the biggest problem of all, because that's where this all leads. But just to continue with the context before we turn to the solutions, what I'd like to also hear about, and maybe Sukumar, you could go first here, is, you know, the designs are getting bigger. Are the schedules getting longer? Is the compute expanding, you know, proportionally to the complexity? So what I hear from you is, from everybody, is there's more work to be done, more high-level complex things to verify on bigger designs. All of these things lead you to more compute, more resources, more people, more time. What's the context? What is that the case? You're getting given more time, or what's? I don't. My history is that it's almost been a constant for 30 years. That time's never changed. But I'm interested to hear your input there, Sukumar.
No, that's true, right? I mean, the business dictates when you actually, you know, tape in a program, or how you do it is up to the engineering teams now, right? Now, there are two pieces to this. One is the human capital, like what you said, right? And the other one is the resources around the machines and how you do verification, how smart you do verification. Now, assuming for a second, and this is the reality, right? Assuming for a second that you don't have infinite time available, right? You have a set duration, because let's be honest, at the end of the day, business dictates your programs, right?
Yeah.
So you can't be late. I mean, if you're late, somebody else has gone and eaten the cake, right? So given that, truly is infinite number of people working in a verification on a program a reasonable answer? Absolutely not, right? So the first thing we need to do is, and since we're talking verification specifically, there are two things we need to do. If you look at the problem today, at least in the SoC space, and it's true in the IP world as well, is first of all the bug classification, right? So it is directly proportionate to how we use verification machines and what kind of people we use, right? So there, in my mind, there are four kinds of bugs broadly, right? You have a basic bare-bone construction bug. You have a basic bug where you try to write into a read-only register and the write happens, right? So a basic bug. And then, of course, the depth bug, where you have a complex, you know, self-refresh and a periodic RComp, and then back-to-back cycles, and then oops, there is a corner case bug, right? And then, of course, the fourth one is the architectural bug. Primarily, that tends to architectural definition differences between multiple different IPs. So these are really the four important bugs. Now, the problem that we have today, and if I look at the industry today in general, the human capital problem is mainly because of the first two bugs, right? So for any program to execute, successfully in a given amount of time or duration, the first thing we got to be careful about and be cognizant of is you need to have a bug budget. Whether you like it or not, the beginning of the program, a verification lead or a verification engineer has the right to say, this is the amount of number of bugs that I'm going to find on this project. Anything more than that is a problem somewhere before me, right? It could be the architecture, microarchitecture design. Now, one of the things that I definitely want the EDAs to go solve is not just the verification problem. Everybody wants to solve the verification problem. But if we can, and I think we do, I mean, there are a lot of other things like formal, and I mean, we can talk about it later, but the issue is once you start going and fixing the microarchitecture definition and the integration problem, the connectivity problem, the first two buckets of the bugs that I talked about are fixed, which means you need less people. So when you actually start planning a program, please plan with a bug budget. I mean, if you're not budgeting your verification bugs, then there's a problem right there. You can't have infinite number of bugs, right? So that's the human capital aspect. The second one is the machines, right? What do you do? Do you do prototyping? Do you do hardware, acceleration? Because simulation is slow, right? How much and what do we do is directly, again, proportional to what kind of verification we want to do, right? The challenges there, again, are twofold, right? Whether you talk about hardware acceleration for a second, or whether you talk about formal, right? Or any other new techniques that we use, what we need to do today is to actually make sure that the bring-up cost is very fast, the bring-up cost is less, and then we actually use that as efficiently as we can, and we are using the simulation platform. historically, we've been so used to doing simulation, we just forget that there are so many other things available. And then we do actually use a lot of other techniques, right? Trust me, I mean, I use pretty much every technique available in verification, right? And yeah, we spend a lot of money on that. The problem though is the efficiency is not there. And today, that is the partnership that the SoC and IP engineering teams have to do. That partnership between the EDA and the engineering organizations will have to improve, and I hope that will be the case.
Cool. Okay. So, Nirmal, I'm guessing you're not going to say you've got infinite resources and infinite human capital then?
Yeah, I agree to Sukumar, right? So infinite resource is definitely engineer's dream. But yeah, to shed some perspective here is we are definitely seeing there is a shrinking in the sizes. Again, this goes back to the typical mindset, right? Which the IP level reuse and integration at SoC is the SoC verification problem. But what we end up is for a reuse chip itself, this integration followed by basic system testing is what we tend to complete when the IPs are maturing. But the system hasn't matured yet. So the IPs are maturing, so we have integrated the stuff, but still the system itself has not been verified thoroughly. So that's the primary aspect, or the team size today is not from the number of IPs or the area of the chip, or I think we should go towards proportion to the complexity of the features itself. So this involves, when I say the complexity here, there are features which are involving multiple layers of validation. It can be as simple as a simple IP level basic verification to how that IP is going to interact with the system and how it's going to give you the overall application realization. So definitely this team size, yeah, we need to work on innovative ways, how to leverage, verification done at different levels. So that's something I think we will discuss once we go to the solutions. The compute, yeah, so it has skyrocketed once the AI engines have started coming in. So what we see is, I think we have hit the roof for the servers, max memory sizes. And I think this is going to be amplified with multiple SoCs and, the future of chiplets and, 3D IC.
Right.
This is going to be really, really area which definitely needs to be looked at. So at least we are seeing 2 to 4x compute growth typically every year, and this is going to be unsustainable. Yeah. The hardware acceleration platform is definitely an area where we are also looking at before tape out, how much test content can I do in this hardware acceleration. Typically, this involves a lot of concurrencies, and this involves multiple teams interactions, and it's a multiple layer of verification, like I said. So we work with SoCs, post-silicon teams, the software teams, and everybody's demand for acceleration is increasing. Yeah, we are seeing very high demand for acceleration, I would say that.
Okay, thank you, Nirmal. I mean, one of the things that intrigues me also is the impact of configurability. It seems like IP, whilst the IP problem has been solved in some senses, the amount of configurability in these SoCs is just, that's also exploding. And obviously you have hard configurability and soft configurability, and having the verification guys want to know at least that the hard configuration parts are correct, right? That's the minimum absolutely you have to do, and hope that if there are any issues, the soft configurability allows you to work around them. But that's something certainly in the last 10 years, it's like exploded. I'm going to, in the interest of time, I'm going to skip now to move on to talk about what technology and methodology approaches are emerging or have emerged over the last few years that are helping to address some of these problems. So talking about really the fact that at the IP level, UVM has really established itself as the main reuse methodology, and that's kind of it's not done, but it's somewhat a solved problem. But UVM doesn't really solve the issue of content reuse. So we've seen recently the rise of portable stimulus to address this, the ability to reuse content. And so maybe Nirmal, you could go again. I think if you've got something to say about portable stimulus and its role in your projects.
Sure, thanks. Yeah, the focus on stimulus and the early adoption of the PSS has really rewarded us. So we started, teaming up with Cadence early, and definitely the stimulus generation and management has been a boon for us in terms of, SoC to SoC, how to leverage test cases, and SoC to a post-silicon, how do we leverage these tests? I still have to admit that we have not been able to, successfully getting the IP to SoC stimulus reuse. Again, primarily this is due to the multiple languages, methodologies, and the various IPs in-house, third party. So this gamut of problem is still, we are still looking at, how do we go about it? Definitely, we are looking at the PSS enhancements, which is being discussed, and we are expecting, this advanced memory management, the new scenario generation, hardware, software interface enhancements. These are really needed for us to create the required system level coverage for the complex SoC. So from a still, our coverage is at system level is still in a nascent stage, I would say. We are still trying to develop, how these coverage can be evolved, to really say, are we done with system verification?
Right.
Yeah.
So Sukumar, do you want to comment on portable stimulus or at least software-driven verification?
Yeah, so so there are two things, right? One, so a decade ago or more, when System Verilog came on board, I think that was truly revolutionary in how we started doing verification, right? The way I look at portable stimulus, it's as big, right? Because this is something that's going to stay, and this is something that's going to become the heartbeat of verification going forward, right? So two things. One, portable stimulus by definition of reusing the test cases across platform is great. But then I also want to be careful, and I also want to call out that the beauty of this is this involves, or this forces us to get more into an architecture-driven verification concept, right? I mean, that is truly what it is all about, right? So we absolutely want to make sure that the architects do the modeling and the verification guys go write the scenarios. And that's exactly how we get to the right system level scenarios. And like what I was talking earlier, right? I mean, with the plethora of IPs coming on board and the system architecture being so complex, this is the solution, period, right? So that's the first point I want to make, is because this will force the verification community and the engineering community in general to go towards an architecture-driven verification, right? Now, the other part of it, like the name says, is the portability of the stimuli, right? So whether it's from your simulation to emulation to FPGA or post-silicon, or whether it's vertical from IP to SoC, because the paraphernalia of the test bench is different, you are going to obviously, see different scenarios. It's not the same thing that you run in simulation and emulation. And the added advantage of you're doing the modeling, you have the architecture right, you're correct by construction, at least from a stimuli perspective, and then boom, go into a different RTL, a smaller piece, a bigger piece, and then see what happens, is the benefit of that, right? And I have been using this quite successfully in some of our programs, and have not started in some other programs, and that's where I want to actually engage more and start doing this. I think, to be very honest with you, this is a verification engineer's dream, and this is what we need to go towards.
Yeah, the what we're seeing, I think, and that it's really emerged over the last few years, and it feels a lot like the emergence of VIP in the in the UVM domain, is that reusable content, in the same way we reuse VIP from project to project. If you could reuse, say, workloads, or and from your own point of view, or maybe in other domains. Pankaj, would you like to describe how portable stimulus plays a part in your SoC projects?
Absolutely, Nick. I mean, as Sukumar was saying, and I think Nirmal also touched upon it, basically making sure that you can bring in the test intent or the application intent as part of the modeling early, as part of the architecture definition itself, that these are the intended use cases, this is how I expect it to work. Getting that in as part of the model and as part of the test definition, and then flowing that through the aspects of what a subsystem or a SoC really needs to deliver, and then having the ability to sort of close on your coverage depending on what you can cover in simulation, target it to a simulation platform, and then look at, okay, these are my complex aspects which cannot be covered in simulation, and I would essentially target some of these verification tests to my Palladium or post-silicon platforms, and having the ability to design that test intent upfront and then sort of portable use it across platforms depending on the simulation throughput requirements that you have is really big. And we see it really helping us with respect to the internal SoCs that we build in order to define the solution. And we also see this really helping as we work with customers.
Cool.
And being able to use it with UVM, I mean, in the sense that you use UVM and then you use software driven and use it in the context of top of operating systems. I mean, all of that really helps.
Yeah, that's an interesting angle we haven't really explored, is, we're talking software driven bare metal, or maybe even higher layers. My experience so far, it's the first step is the bare metal, because that's the natural domain or the next step for verification people from the hardware level. So, but I think there's a whole other level of where you've got some part of either the I/O software, the drivers, the maybe the UEFI or whatever, that you actually drive test payloads at that level, because that's another level of reusability, and you can get some big benefits from that. What about hardware acceleration and FPGA prototyping? How big a part do they play in are they, is that they really for software validation, or for hardware software verification? How do you use those sort of platforms? Nirmal, can you comment on that?
Yeah, so on the typically what we are primarily focusing on acceleration of the FPGA prototyping platforms are two use cases I can think of. One is overall system security, which is primarily we have so many processors now in a system, and this content access protection is a primary challenge for the resilience from hackers. So this typically is it's a parallel development with software where we enable them and we work with them to make sure this whole system security is validated. So the other one is the new use cases. Typically, the new use cases comes with a lot of assumptions starting from architecture to IPs to systems. Typically, this is where we start, working with the teams early in the game, where we try to clearly document all these assumptions and validate them at a different layers. So a recent example I can think of is the always-on camera. Another way of waking up the phone. Once you pick up the phone, it turns on seeing your face. So we thought, okay, we have a camera, so why don't we just make it simply always on? So we just started off that, and then we started seeing a lot of complexities which bring up where where the software has to run, and that part has to be always on, and there are so many other drivers and other applications which have to work together to make this application to work. So it's definitely the FPGA prototyping and acceleration is the way to go. We definitely see a major of our verification will move towards that area.
And what about a hybrid model? So one option is because capacity is a problem with hardware because it's expensive. One option is to take the CPU subsystem out and you run that in a TLM model and connect the two with a transactor, which we call a hybrid. Is that something that's obviously there's specific scenarios where the performance of that isn't very good, but there are also scenarios where the performance of that is exceptional because you get software running very fast on the TLM models or fast models. Is that something you use, Nirmal?
Definitely, need for speed has always been there for SoC verification. So we want our tests to run complete, definitely not in weeks, right? So we want in days to complete our verification regressions.
Cool.
As we discussed, we have been reaching the limits of compute memory. Definitely, there is a trade-off for coverage, which we end up paying. So faster test bench and transactions will definitely improve the overall system coverage. Again, going back, these models have to be, properly validated. Like, from architecture, these have to be, developed. And I'm sure, definitely, this is one area which definitely we can transition our system verification in the simulation world. Before going to the acceleration or the prototyping.
How about you, Sukumar? How do you see hardware platforms being used, and is hybrid interesting? Is it an option?
Yes. So two parts to the answer, right? One, when you start building bottoms up, IP to SoC, it's very efficiently used. First of all, it's a given from a software perspective, right? For development and verification, that's just it's just a given. There's no question about it, right? It's just a wonderful platform. Yep. From an IP hardware perspective, to build IP FPGAs and to actually go behind the box it's a great way of validating because you are finding bugs much faster. It's a smaller piece of logic. And yes, I am a big fan, and we do use hybrid models, right? Because hybrid models does give, at the end of the day, it's all time, right? It's faster. You just take a big piece out of your FPGA and then make it much more efficient for what you want to do. Because at the end of the day, you don't need everything to do every piece of verification, right? What I have seen the biggest challenge though is to even put bigger pieces of SoC where, like I was talking earlier in terms of system architecture, right? Like-minded IPs, if I can call that, right? And then put them together to actually run real system level scenarios. I would love to do that, and I probably at some point would want to go there. I've been trying. The issue is debug, right? The debug cost is too high. And when you have such a high debug cost, bring up cost is still manageable, I feel. The debug cost is quite high. Unless we solve that problem, it's going to be a challenge. But is that the right direction to go? Absolutely. Are we there yet? I certainly am not.
That's it's interesting because what that tells me is that there's not just a move to some of the workloads being in software, it's a massive move, right? Because what you're saying is that predominantly it becomes a software problem, is the SoC verification problem as much as a hardware, that you're verifying the hardware, but the actual mechanisms are mostly software driven. Pankaj, maybe you could give some color, because I know you've got some experience and where it's maybe not so good.
Yeah, absolutely. I mean, as we really look at it from simulation to emulation to FPGA prototyping, we go from kilohertz to megahertz to multi-megahertz. And as we go into hybrid, we go into hundreds of megahertz, because for the use cases where you can apply it, it really gives you the verification throughput. I mean, you can really run your systems fast. So things like wherein you have the bulk of the SoC running in emulation or your FPGA system, and you need to verify it in the context of a Linux boot or an OS boot, and then you need to run some specific applications or need to build some drivers. In that context, we use it and we see our customers use it very efficiently. So there, I mean, the cost of initial bring up that could be hours can actually be done in minutes. So that definitely helps. And I mean, with Linux, it's in that range. But when we talk about mobile systems with Android, doing it in a purely emulated or an FPGA system, prototyping system, is still taking a lot longer. So early bring up can be done in hybrid, and then a lot of the customers, like for example in mobile, they want to run benchmarks in order to see, okay, they get the right CPU performance, the right GPU performance, the right memory performance, and they run things like Geekbench and all these other benchmarks. So I mean, I see that EDA is now providing the technology to be able to bring up your OS early, and then there is the ability to shift into a purely cycle accurate setup and then run your cycle accurate benchmark. So, I mean, I do see a shift to that, though people still use it. I mean, the hardware assisted systems are also used for hardware verification, but a lot of the hardware software co-verification.
Cool. I want to go on to a topic I think a lot of people will be interested in, which is machine learning and how machine learning is being infused into EDA tools. Cadence has applied ML in simulation, in the formal tools, recently acquired a company called Verifighter who have an ML tool for identifying the most probable check-in, which will, accelerating root cause debug. How do you see ML being applied in the SoC verification space? Nirmal, do you want to take that?
Yeah, so definitely regression management is a huge task for us before tape out. We want to make sure we have run all the required scenarios, and we are able to qualify the maturity. So with so many IPs integrated and so many scenarios being generated, the stimulus management, with so many engineers there, So we have seen that finding these failure analysis using ML definitely helps. So there have been certain in-house, tools which we have developed and we have been using them. But definitely, we look forward if EDA can, solve it for us in a most commercial way. The other areas which we definitely look at is like this expert systems, which definitely can help, for the debug, where pretty much most of the engineering time is spent on, why did a test fail? Why did a test fail in this particular regression? So that's where we see, a lot of expert systems can definitely help in, bringing the intelligence or the machines, trying to get process as much as data, and then give us, okay, this is the probable cause, and we can take that and leverage it.
Cool. Sukumar, what are your thoughts on ML and how it might impact your job?
I think verification is tailor-made for ML, right? I mean, both structural design and verification, for that matter, are tailor-made for ML. We do have a lot of in-house stuff that we keep doing. There are two pieces again. One is the verification execution, and the other one is verification planning, right? And we don't want to forget the latter. So execution is typical, right? I mean, I know a lot of EDAs are working on this as well, whether it is, making your regressions better, choosing less number of tests to hit the same amount of coverage, making your debug smarter, figuring out which exact turn-in messed up my code or whatever that is, right? That is one aspect of it. The other aspect of it is based off of, and most of us do this, right? Based off of like projects in the past. What is the regression prediction? How does my coverage look like if I have a goal of, I don't know, 2 quarters program execution? Can I actually go and predict how well I am 1 quarter down the line and 2 quarters down the line? And what is my bug prediction? What is my regression prediction? What is my coverage prediction, right? These are verification planning tools that are of immense help for program execution, right? I mean, this also feeds into all the other questions that you asked about earlier, and we talked about in terms of resources, in terms of how much do I need to actually execute, and how successful am I going to be, right? So both the verification planning aspect as well as the verification execution aspect, right? And once we get more into the verification execution aspects, there are a lot of problems we can solve, right? I mean, today we talk about really hard problems like GLS, right? If you want to really do GLS, I mean, how do you choose your test? Which test do you know that will run on GLS, right? These are typical ML problems that we can solve, right? Very hard problems, easier said than done, but those are the ones that we have to go behind.
Yeah, one of the things I always thought about was the classification of IP. If you're looking at IP, just IP verification, can you classify an IP into a category to be able to predict how long it would take to verify? Because some IP have very complex control paths, some are very simple, and it's usually the control paths that actually make it hard to verify. And so it would seem ML would be a very good fit for that. And whether that becomes then, you can say a whole SoC, well, I've categorized the planning expectations of these, and you learn from the past. So the challenge is, in my mind, was also keeping enough data from previous projects, because the data problem's huge already on the single project. But yeah, interesting. What about formal tools being applied or scaled up to SoC? Does one of you want to take that and talk about any thoughts about formal application in SoC?
I've used formal pretty well. So although since you asked the question specifically for SoCs, right, it has a very specific role and place in SoC as opposed to IP, right? I mean, IP, I will argue the formal space is much, much, much bigger. There are specific things we can do, right? One of the biggest things that I've realized with formal is The fact that it helps me not run as much of dynamic simulation, and actually on day 0, day 1, I can go and find out, remember the bug classification that I was talking about? If I can actually find out all those activity bugs, right, on day 1 or day 2, I mean, that's like weeks or even months of simulation savings for me, right? That's the beauty of formal at SoC, right? Those are absolutely the right things to do. I've done that, and I've done that very successfully. And trust me, it saves a lot of schedule, right? That's point number 1. Number 2, one of the challenges that we have is, and I will tell you guys, right, all the EDAs as well, is don't sell this to verification team. Sell this to the microarchitecture team. Sell this to the RTL guys, right? Because it's not just verification. Somehow there is this belief that formal is a verification tool. Sure, it does find you bugs, but then you got to have your microarchitect and RTL engineer and or RTL engineer sitting with you to actually figure out what's going on. This is an example of truly a team effort, right? So we got to actually rebrand formal to basically say this solves your SoC problem, right? That is one of the biggest things, because when you actually go from a base to derivative, right, your reverse connectivity, you're basically saying, okay, so what did I change from, point A to point B when point B changes are very small, right? That's not necessarily a verification problem, right? So that is where we need to go behind. The application is high, the return on investment is very high. The difference is, in an IP space, it has got a lot more applications. In an SoC space, it has its own specific area that we can actually target.
There was a lot of activity maybe 10 years ago that maybe there would be automated assembly of SoCs, and that in some ways would mitigate the problem you described in terms of human integration of the SoC, but that doesn't seem to have manifested at all. I don't hear of companies automating the assembly in any big way. Is that anyone want to comment on that? That's something either of you two guys have looked at as a technology, or as a company, should I say, automating the integration, or is it still predominantly done?
Well, I will tell you that we have looked at it.
Right.
I can tell you that I don't know if anybody has been as successful. I mean, I thought maybe 8 years ago, 10 years ago, people thought this will be the next big thing and people can just automate the whole thing. Honestly, I don't know of anybody who has been quite successful, and I haven't either.
Yeah, neither do I. I mean, I actually see that people attempting it, and there are a lot of complexities in terms of being able to assemble, packaging the IPs correctly, getting all the right data, and then all that. I mean, it's just.
Okay. Nirmal, any comments on formal application at SoC? Any thoughts? Finally,
Yeah.
we're coming towards the end of our discussion.
Sure, Nick. So definitely formal has been a focus in our company also. Primarily, we are focusing how do we accelerate dynamic SoC verification. Pretty much, we are looking at all the avenues, starting from sequential equivalence, where we want to make sure the IPs are sequentially equivalent. We are not talking about the big systems getting integrated, but there are small IPs which really come into SoC level. And definitely on the late ECOs, sequential equivalence is our primary weapon for verifying these late ECOs. And recently, we have tasted some success with the low power connectivity, which is becoming, I think we are getting some solutions from the EDA. We definitely look at, this power domain crossing is a problem which with this hierarchical UPF, and we have this so many domains, and on top of it, we have this restructuring the RTL for the physical design. So we have a multiple layer, these power is completely changing, which is where we are definitely looking at formal to come and help us a lot. And the other areas which we have been trying is on the sequence validation. Primarily, before even I run a sim, is this a sequence going to be giving me the required output? So these are some areas which we are definitely looking at.
Cool. Okay. Well, we're running out of time. I'm just like to say thanks, you guys. This has been really interesting, and actually be good to actually talk a bit longer. If only I could come to India, right? One day soon, I hope I'll be able to come. I don't know if we've got any questions, but if Shreya, do you want to close things up?
Yes. Thank you, Nick. Thank you, panelists, for that discussion. I'm sure all of us are going to go back and think of all our resources and splitting up between resources, whether people or IT resources. Okay, thank you. So we come to the closing section of DVCon India 2021, and I will hand over now to Pradeep. And if I can share my slide, please.